Hello and welcome to the Chemistry Academy. In this video we're going to go over acid-base titration calculations. This would be helpful for actually National 5, higher or advanced higher, because you do titration calculations at all of those levels. And yeah, for the acid-base ones, a titration where you're reacting an acid with a base, it basically all works in the same way. But this is mostly aimed at National 5, so let's get into it. So I'll put a question from an SQA exam paper on the screen so you can have a see of the information that I'm reading off my iPad. But for most of the titration calculations that you'll get, they follow this standard structure where you get given a table of results that will look a bit like this. You get given a balanced equation, and then you get asked usually the question in 2 stages. So the first stage, which isn't actually shown on this question because this is an old exam, but usually the first part A is to calculate the average volume of whatever is in your burette that should be used in the calculation. So this is calculating the average volume of the standard solution that was needed for the titration. Remember, a standard solution is a solution of accurately known concentration, and that is what goes into our burette when we're doing a titration. So to calculate the average volume of the standard solution, the results table can quite often make it look a bit confusing, but there's so many numbers in it that you don't actually need. So the first titration is always ignored. It's always sometimes known as the rough. So we do that first titration to give us a rough idea of where the end point is going to be, so that then our titration repeats that we do after that can be more accurate. So I would recommend writing this on your exam paper when you are doing the questions. And the first titration you never need, so just scribble that whole line out. Okay. The other thing that we never actually need to pay attention to when we're doing the calculation are the burette readings. So the burette readings are only there really for the person doing the practical experiment, so they can keep track of how much standard solution they've added. So because of that reason, we can also score out the burette reading columns or rows, depending on which way the table's arranged. So then that leaves us with 2 numbers, and those 2 numbers are the numbers that we will calculate the average volume from. So all we have to do then is add them together and divide by 2, which would give us 16.0 centimetres cubed in this case. Remember, your average is only calculated from the concordant results. So those are the results that are within 0.2 centimetres cubed of each other. So remember that word, concordant. Okay, so sometimes we need to do 4, 5 titrations before we actually end up with concordant results that are within 0.2 centimetres cubed of each other. So if you do get given a table of results that has more than the rough titration and the 2 repeats, just pick 2 of the results that are within, or any of the results that are within 0.2 centimetres cubed of each other. So that's the first stage of the calculation. The second stage of the calculation is the one that's actually on the question here. Is calculating the concentration of limonene in the household cleaner. So you can see from the picture, the household cleaner is the sample, that's what we're trying to calculate the concentration of, and the bromine solution that was in the burette is our standard solution, which we've just calculated the average volume for. So what I like to do when I'm reading through the question is to write any numbers or variables on next to things in the equation. So because the question says to calculate the concentration of limonene in the household cleaner, I know that limonene will be this one because this is obviously bromine. So I know I'm trying to calculate the concentration of that. Then for the rest of the information, we look at the picture. So we can see that the concentration of the bromine solution is 0.5 moles per litre. So underneath bromine, I'm going to write C equals 0.5 moles per litre. We're then also given a volume in the picture, which is the volume of the household cleaner. So that's what the limonene's in. So that would be our volume for that, 20 centimetres cubed. But we always need to convert our volumes into litres. So we need to divide them by 1,000, which would give us 0.02 litres. The volume of bromine is what we actually calculated previously, so that's 16.0 centimetres cubed, but again we need to convert it into litres, so we need to divide by 1,000, so that becomes 0.016 litres. Okay, so once I've written that information next to the equation on the question, then what I do is take the two chemicals that I'm interested in and write their formulas down again underneath. And then I put the mole ratio in the middle. So there's no number in front of the limonene, which means there's only 1 mole of it in this chemical relationship or chemical reaction. And then there's a 2 in front of the bromine, which means that there's 2 moles of bromine required. Okay. We're dealing with volumes and concentrations, so the mole relationship we're going to be using is NCV. So I'll list those variables underneath here. And then I pull my numbers down again to my little list. So I've got a question mark at that concentration. This is 0.02 litres. Then on this side, concentration of 0.5 moles per litre. And then a volume of 0.016 litres. It's a good idea to write the units down because it reminds you, if you've not converted the volumes into litres, because you can see the concentrations, moles per litre, which is why we need our volume in litres, because the units always need to match up for calculations. So if we then look, we can see we can calculate the number of moles of bromine here. So you should never usually start a calculation in chemistry knowing the number of moles of something. That's usually the first thing you need to do in every chemistry calculation, is calculate a number of moles, aside from like EH equals Cm delta T and stuff. But for any standard chemistry calculation from a balanced equation, you would usually start by calculating a number of moles. So we can do N equals CV, so 0.5 times 0.016. So we put that in my calculator. That gives you 8 times 10 to the minus 3. It's okay to write numbers in scientific notation in your chemistry exam. If you've done this on a phone calculator and you get 0.008, that's also fine. You can write it like that as well. Times 10 minus 3, so that goes up there. Now we can use our mole ratio to move across. So it's 2 moles to 1 mole. So if we're going from 2 to 1, that means we're dividing by 2. So I need to divide this by 2, which gives us 4 times 10 to the minus 3, or 0.004. Again, either is fine. Now we've got the moles here and the volume, we can work out the concentration. So C equals N over V. So 4 times 10 to the minus 3 over 0.02. That gives us 0.2, and it'd be moles per litre. Now the units are usually always given to you in question, so you can always double check the question for what your final units are before you write them down, or because the units are given in the question, the SQA actually don't expect you to write them, so you could just leave them. So the units are not always required. If the units aren't given in the question, then they are required and you need to work out what they are, and you'll get an extra mark for doing that. Okay, so that's an example of a standard titration calculation. We'll go through another example of a standard one, and then we'll do a couple examples where you're maybe not calculating a concentration, you're calculating something else. But I'll just show you how a similar method of writing down the numbers you're given can help you see where you can actually start the calculation off. So here's our next example, and again I'll put the question up on the video so you can see what one we're doing. This one, the results table's inverted this time, so it's the different way around, and sometimes that can throw people off as well, so just bear in mind that you can get the tables in 2 different formats, so just kind of get used to looking to see what the labels are. The first part of this question though is to name the most appropriate piece of apparatus to measure the 10 centimetre cubed of sodium hydroxide solution. So that is our sample, and we always measure our sample using a pipette. I do have a separate video on the practical aspect of the titration. If you want to go and have a look at that video, you can find it on my National 5 Chemistry or higher playlists. And then the second part is so they tell you what the average volume of oxalic acid that should be used to calculate the sodium hydroxide concentration is. They tell you that's 15.6 centimeters cubed, but then they ask you why only the results of the second and third titer are used to calculate this average. So if we look at our results table, remember you never use the first titration because it's a rough and it's never concordant. We don't ever need the burette readings, so we can score them out, which means any average is calculated from these two numbers that are left, and they are concordant. They are within 0.2 centimeters cubed of each other, which is why they are the only two values that are used to calculate the average, because they are the only concordant results. So that's what you would want to say for your answer in this, is that they are the only concordant results, okay? Or the average is only ever calculated from concordant results. So then we get onto the actual calculation bit. Using the average volume of oxalic acid is 15.6 centimeters cubed. So they've given us a volume of oxalic acid. So I'm going to write V equals 15.6 centimeters cubed. Remember, we always need to times it and divide it by 1,000 to convert it into litres. So that'd be 0.0156 litres. And then it wants you to calculate the concentration in moles per litre of the sodium hydroxide solutions. This is sodium hydroxide here, so I put C equals question mark to remind me that that's what I'm trying to calculate. Switch to a blue pen this time. So now we look at the picture. So we've also got the concentration of oxalic acid, which is 0.1 moles per litre. That's from the picture. Then we've got a volume of sodium hydroxide solution. So 10 centimeters cubed divided by 1,000 would be 0.01 litres. So I'll take the chemical formulas of the two chemicals I'm using. Again, it seems like a lot of writing here, but it's actually not as much as it seems. Our mole ratio, there's no number in front of oxalic acid, so that's just a 1 mole. 2 in front of the sodium hydroxide, so that's a 1:2 ratio. N equals V equals C equals. I've written them in a different order this time, but it doesn't really matter. That I'll change it back just to keep consistency. So the concentration of this was 0.1 moles per litre. The volume 0.0156 litres. Again, keep writing down your units so that it makes you doubly sure that you've actually converted. So we can see this time we're starting on this side. So N is equal to CV. So 0.1 times 0.0156. I got this new calculator and I'm dead chuffed with it because there's a wee pen and you can actually write your working on here. I don't know if you can see that, but anyway, I feel like 40-year-old women with it, but never mind. And then you can clean it off and start some new working. Anyway, sorry, back to the question. So 0.1 times 0.0156 gives us 1.56 times 10 to the minus 3. Again, you don't need to write it in scientific notation. You could have had 0.00156 and that would have also been fine. Going across, it's 1 to 2, so we need to times by 2 this time. So then if we times that by 2, that gives us 3.12 times 10 to the minus 3. And then C is equal to N over V, so that would be 3.12 times 10 to the minus 3 over 0.01. Which is 0.312, and that would be in moles per litre as well. And that's you. So that's the two kind of standard titration calculations, but we'll do a couple now, like I said, that are a bit different, and show you how doing this process can still help you attack those questions. Okay, so let's move on to the next question. So again, I'll put it on the screen. And the first question again is asking the most appropriate piece of apparatus to measure out the sample of water. Again, you're always measuring your sample using a pipette. Pipettes are the most accurate ways of measuring volumes, but they can only do exact volumes. So for the 20 centimetre cube sample, we would need a 20 centimetre cube pipette. If it just so happened that you didn't have a 20 centimetre cube pipette, the next best thing would be a burette. Okay. And then part 2, explain why only the results of titration 2 and titration 4 are used to calculate this average. So if you look at the results table, you can see that 2 and 4 are the only results that are concordant with each other, so within 0.2 centimetres cubed. So again, your answer for that would be that the average is only calculated from concordant results. Then part 3, calculate the number of moles of silver nitrate in 8.05 centimetres cubed. So that's a volume of silver nitrate. Okay, and again, we always convert our volumes into litres, so we need to divide by 1,000, so that'd be 0.0805 litres. And it wants us to calculate the number of moles, so I'm going to put n equals question mark. And then if we look at our picture to see if that can give us any more information, it's talking about the silver nitrate, and if we look at silver nitrate in the picture, it gives us a concentration. Okay, so what we can see from this is that we can calculate the number of moles of silver nitrate because we've got a volume of silver nitrate and we've got a concentration of silver nitrate. So this is not a full titration calculation from a balanced equation. This is just an NCV calculation, which is why you'll notice it's only worth 1 mark. So sometimes looking at the marks assigned to the calculations can give you an idea as to how short or long the working is going to be for them. So n is equal to CV. We've got 0.02 times 0.0805. If you put that into your calculator, you get 1.61 times 10 to the minus 3. And that's number of moles, so you could just put moles. Okay, and that is that one. So it is a bit harder when it's not a full-blown titration calculation because you can't really get into sort of flowy rhythm. It sometimes takes a bit of thinking time, but by writing down the numbers you're given, you could have also put silver nitrate up here just to keep us right. Obviously we've also been given information in the picture of a water sample, so we could have had something to do with water over here and see that we had a volume of 20 centimetres cubed, which would be 0.02 litres, but we didn't have enough other information about the water to do any calculation for it. So sometimes seeing that you don't have enough information is an indication that you don't need to calculate anything for that chemical. We will do one more that's slightly different, and then hopefully that will give you a good understanding of the titration calculations and how you can go about them. Last one, and again I'll put the question on the video so you can see what it is. The first part of this looks like it's going to be a standard titration calculation because it asks us to calculate the average volume of oxalic acid that was required to neutralise the sodium hydroxide solution. So I've not written the results table up, but again you would score through the rough titer row in this case, score through the initial and final burette reading columns, and then you should see that the only 2 concordant results you're left with for the volume used are 14.9 and 15.1. So you would add those together, 14.9 plus 15.1, divide by 2, and then that would give you an average volume of 15.0 centimetres cubed. Then part D says oxalic acid is found naturally in rhubarb a piece of rhubarb was found to contain 1.8 grams of oxalic acid. So anything in grams is a mass. It's a mass of oxalic acid. My spelling is horrendous today. So we've got a mass of oxalic acid, 1.8 grams. And then it wants us to calculate the number of moles of oxalic acid. So N equals question mark. And then it says the formula mass of oxalic acid is 90. The formula mass is the gram formula mass, GFM. So by writing down all the numbers it's given us, we can see that we actually need to use the NM-GFM relationship here. So N is equal to M over GFM. You do get that at the front of the data booklet if you ever do forget it. And then of course you've got the triangles that you can try and learn if you wish. So M is 1.8, GFM is 90. So then if we do 1.8 divided by 90, we get 0.02, and that's the number of moles, so that'd be moles. And that's that one. So again, this is why it's helpful to write down the numbers you're given in the question next to the letter variables that are associated with them, and it can really give you good indication as to what mole relationships you need to use and where you can actually even start your calculation. So I hope you find that helpful for your titration calculation knowledge. If you did, please give it a like, don't forget to subscribe, and I'll see you soon.